Welcome to an extraordinary journey beyond our world, where humanity dares to dream of reaching the stars. Interstellar travel, once confined to the pages of science fiction, now beckons as a profound challenge for our species. The vast distances to even the nearest stars, spanning millions of miles, dwarf our greatest achievements in space exploration. Consider this. A journey to Proxima Centauri, our closest stellar neighbor, would take tens of thousands of years with today's technology. Yet, the question persists. Can humanity transcend these cosmic barriers, or are we destined to remain forever bound to our solar system? In this exploration, we will unravel the science, technology, and philosophy of interstellar travel. From the boundaries of our solar system to revolutionary propulsion concepts, we will examine the obstacles and possibilities that define this quest. We will delve into the human spirit, its resilience, curiosity, and ethical dilemmas, as we ponder what it means to venture into the unknown. Join us as we ask, are we merely fish in a cosmic aquarium, or can we become explorers of the galaxy, charting a path to the stars? Let us embark on this voyage together into the vastness of the cosmos. Imagine standing at the edge of our solar system, where the influence of the sun begins to fade. This boundary, known as the heliopause, marks the frontier between our cosmic neighborhood and the vast interstellar medium. The heliopause is where the solar wind, a stream of charged particles from the sun, meets the interstellar winds of the galaxy. This invisible line, located about 75 billion miles from Earth, forms the outer edge of the heliosphere, a protective bubble that shields our solar system from high-energy cosmic rays. It is a gateway to the unknown, a threshold humanity has only begun to cross. The heliosphere is a dynamic structure, sculpted by the sun's relentless output. As the solar wind travels outward, it slows dramatically at a region called the termination shock, roughly 60 billion miles away. Here, the solar wind's speed drops below that of sound, creating a turbulent zone before it reaches the heliopause. Beyond this boundary lies the interstellar medium, a sparse sea of gas, dust, and plasma from distant stars. Understanding this transition zone is crucial, as it reveals how our solar system interacts with the broader galaxy, setting the stage for humanity's first steps into interstellar space. Humanity's first emissaries to this cosmic frontier are the Voyager spacecraft, launched in 1977. Voyager 1 and Voyager 2, designed to explore the outer planets, ventured far beyond their original mission. In 2012, Voyager 1 crossed the heliopause, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. These spacecraft, traveling at 38,000 miles per hour, have journeyed over 14 billion miles, carrying messages of humanity's existence to the stars. Their achievement is a testament to our curiosity and ingenuity. The crossing of the heliopause was not merely a technical milestone, it offered profound scientific insights. As the Voyagers passed this boundary, their instruments detected a sharp increase in cosmic rays, high-energy particles from supernovae, and other cosmic events. The magnetic fields shifted, aligning with the galaxy's broader structure. and the density of plasma rose significantly. These changes confirmed that the spacecraft had left the Sun's protective embrace, entering a realm where the rules of the cosmos shift. The Voyager's data continues to shape our understanding of this distant frontier. Yet, the heliopause is not a fixed line, but a dynamic, fluctuating boundary, influenced by the Sun's 11-year activity cycle. During periods of high solar activity, the heliosphere expands. During quieter times, it contracts. This variability complicates our understanding of where our solar system truly ends. The Voyagers, now over 40 years into their journey, are powered by decaying plutonium, with their signals expected to fade by the early 2030s. Their silence will mark the end of an era, but their legacy as humanity's farthest explorers will endure. The heliopause represents more than a scientific milestone. It is a symbol of humanity's ambition to reach beyond our origins. Crossing this boundary has shown that we can send machines into interstellar space, but it also highlights the immense challenges ahead. The Voyagers have traveled less than 1/10,000th of the distance to the nearest star, Proxima Centauri, 4 light-years away. As we stand at this cosmic threshold, we must ask, how will humanity itself bridge the vast gulf to the stars? The heliopause is just the beginning of our interstellar odyssey. Beyond the familiar planets of our solar system lies a realm both vast and enigmatic. The scale of our cosmic neighborhood extends far past Neptune, into regions that challenge our understanding of where the Sun's influence ends. The Kuiper Belt, a vast ring of icy bodies beginning about 3 billion miles from the Sun, marks the first frontier. This region, home to Pluto and countless other objects, stretches for billions of miles, a frozen archive of the solar system's formation. Its icy remnants hold clues to the early days of our cosmic home, preserved in a deep freeze since the dawn of time. The Kuiper Belt is a treasure trove of celestial relics, populated by dwarf planets and comets that orbit in the Sun's distant reaches. Pluto, once considered the 9th planet, is merely one of many icy worlds here, alongside Haumea and Makemake. These objects, some as large as small moons, are composed of ice and rock, remnants of the solar system's primordial building blocks. The Kuiper Belt extends to about 7 billion miles from the Sun, a distance so vast it dwarfs the orbits of the inner planets. Exploring this region reveals the complexity and grandeur of our solar system's outer edges. Beyond the Kuiper Belt lies the Oort Cloud, a theoretical spherical shell enveloping our solar system. This distant cloud, thought to begin some 75 billion miles away, may extend up to 1 light-year, nearly a quarter of the way to the nearest star. The Oort Cloud is believed to contain billions, perhaps trillions, of icy bodies, the source of many long-period comets that visit the inner solar system. These objects, untouched for billions of years, may carry material from the Sun's birth or even other stars, offering a glimpse into the cosmic processes that shaped our world. The The Oort Cloud remains a mystery, as no spacecraft has reached its immense distance, and direct observation is nearly impossible. Its existence is inferred from the paths of comets that swing through the inner solar system, their orbits hinting at a distant reservoir. This vast, unseen cloud defines the true boundary of the Sun's gravitational embrace, marking the edge where our solar system blends into interstellar space. The Oort Cloud scale challenges our imagination, reminding us how small our planet is within the cosmic tapestry, yet how profound our quest to understand it. Among the mysteries of these outer regions is the hypothesis of Planet 9, a massive, unseen world thought to lurk beyond the Kuiper Belt. Astronomers propose its existence to explain the peculiar orbits of distant objects, suggesting a planet 10 times Earth's mass, orbiting hundreds of billions of miles away. If real, Planet 9 could reshape our understanding of the solar system's formation. Its elusive nature fuels debate as scientists search for evidence in the vast darkness. This potential discovery underscores the unknowns that still linger within our own cosmic backyard. The Kuiper Belt and Oort Cloud are more than distant frontiers. They are windows into our origins and stepping stones to the stars. These regions hold secrets of the solar system's birth, possibly containing material from other stars that mingled with our own billions of years ago. As we ponder interstellar travel, understanding these outer realms is crucial, for they mark the first steps beyond the planets. They challenge us to think bigger, to imagine a future where humanity's reach extends not just to these boundaries, but to the galaxies beyond. The dream of interstellar travel hinges on a fundamental challenge: speed. According to Albert Einstein's theory of relativity, nothing with mass can reach or exceed the speed of light, approximately 186,000 miles per second. This cosmic speed limit imposes a formidable barrier, as the energy required to accelerate a spacecraft increases exponentially as it approaches this threshold. To reach even the nearest star, Proxima Centauri, 4 light-years away, would demand unimaginable energy. This universal law shapes the daunting reality of venturing beyond our solar system. Current spacecraft pale in comparison to this cosmic limit. The Voyager 1 spacecraft, humanity's farthest traveler, moves at 38,000 miles per hour, a mere fraction of light speed. At this pace, reaching Proxima Centauri would take over 70,000 years, far longer than recorded human history. Even the Parker Solar Probe, the fastest human-made object, achieves speeds of 190,000 miles per hour near the Sun. Yet, even at this blistering pace, a journey to Proxima Centauri would still span over 6,000 years, underscoring the vastness of interstellar distances. The primary obstacle to faster space travel lies in energy. Traditional chemical rockets, like those that powered the Apollo missions, rely on burning fuel to generate thrust. However, their efficiency is limited, with exhaust velocities reaching only 3 miles per second. To achieve the speeds needed for interstellar travel, a rocket would require an impractical amount of fuel. The more fuel added, the heavier the spacecraft becomes, necessitating even more fuel in a frustrating cycle known as the rocket equation. This inefficiency confines chemical rockets to short-range missions within our solar system. To overcome these limitations, scientists have explored alternative propulsion methods. One promising concept is the solar sail, a lightweight, reflective surface that harnesses the pressure of sunlight to propel a spacecraft. By capturing the momentum of photons, solar sails require no fuel, offering a path to sustained acceleration. However, their thrust is minimal, and their effectiveness diminishes as they move farther from the sun. Even with advanced designs, solar sails would take centuries to reach nearby stars, making them impractical for human interstellar voyages in the near future. A more ambitious idea involves laser-driven sails, as proposed by the Breakthrough Starshot initiative. This concept envisions powerful ground-based lasers beaming energy to a small, lightweight sail, accelerating it to 20% of the speed of light. Such a craft could reach Proxima Centauri in just 20 years. However, the challenges are immense, constructing lasers of unprecedented power, ensuring pinpoint accuracy over billions of miles, and protecting the sail from collisions with interstellar dust. These hurdles highlight the gap between vision and reality in high-speed space travel. High speeds introduce additional complications, particularly the risk of collisions with interstellar particles. At 20% of light speed, even a speck of dust could devastate a spacecraft, releasing energy akin to a small explosion. Shielding technologies, such as magnetic fields or advanced materials, remain theoretical and untested at such velocities. Furthermore, the effects of relativity become significant. Time aboard a fast-moving spacecraft would pass more slowly compared to Earth, creating complex navigational and communication challenges for any crewed mission venturing into deep space. The cosmic speed limit also raises questions about energy sources. To approach light speed, a spacecraft would need an energy source far beyond chemical fuels. Concepts like nuclear propulsion, which could theoretically achieve higher efficiencies, are still in early development. Antimatter engines, offering near-perfect energy conversion, remain speculative due to the scarcity and cost of producing antimatter. Each proposed solution pushes the boundaries of physics and engineering, reminding us that interstellar travel demands breakthroughs that are currently beyond our technological grasp. The cosmic speed limit is not merely a physical barrier, but a challenge to human ingenuity. While today's technology confines us to glacial paces across the stars, the ideas of solar sails, laser propulsion, and beyond offer glimmers of hope. These concepts, though distant, suggest that with innovation, humanity might one day shrink the vast gulfs between stars. As we explore these possibilities, we confront the profound question: can we redefine our place in the universe, or will the speed of light forever anchor us to our solar system? The journey to the stars begins with overcoming this ultimate limit. In 1977, humanity launched two extraordinary emissaries into the cosmos, Voyager 1, and Voyager 2. These spacecraft, designed to explore the outer planets, embarked on a journey that would redefine our reach into space. Taking advantage of a rare alignment of Jupiter, Saturn, Uranus, and Neptune, an event occurring once every 176 years, the Voyagers set out to uncover the mysteries of our solar system. Their mission, initially planned for 5 years, has spanned decades, carrying humanity's aspirations to the edge of interstellar space. The Voyager's journey through the outer solar system was nothing short of spectacular. Voyager 1 visited Jupiter and Saturn, revealing their turbulent atmospheres and intricate moons. Voyager 2, the only spacecraft to explore Uranus and Neptune, unveiled their icy mysteries and delicate rings. Together, they sent back images of worlds previously unseen, from Jupiter's Great Red Spot to Neptune's ethereal blue haze. Traveling at 38,000 miles per hour, these probes ventured beyond the planets, becoming humanity's farthest-reaching explorers, bound for the stars. Aboard each Voyager is a remarkable artifact, the Golden Record, a gold-plated disc carrying a message from Earth. This time, capsule contains sounds of nature, music from diverse cultures, and greetings in 55 languages, curated to represent humanity's essence. Images of our planet, from mountains to cities, are encoded alongside mathematical and scientific knowledge. Designed as a cosmic greeting card, the Golden Record speaks to any intelligent life that might encounter it, offering a glimpse of who we are and where we come from in the vastness of the universe. The Voyager's journey did not end with the planets. In 2012, Voyager 1 crossed the heliopause, entering interstellar space, followed by Voyager 2 in 2018. Now, over 14 billion miles from Earth, they continue to send faint signals powered by decaying plutonium. These signals, traveling across the vast distance, provide data on the interstellar medium. However, their power is fading, and by the early 2030s, communication will cease. The Voyagers will drift silently, carrying their golden records into the cosmic void for billions of years. The Voyager's endurance is a testament to human ingenuity. Built with technology from the 1970s, they have outlasted expectations, operating in the harsh environment of space for over 4 decades. Their success owes much to precise engineering and gravity assists from the outer planets, which slung them toward the stars. Yet, their journey also reveals our limitations. Even at their remarkable speed, reaching Proxima Centauri would take 70,000 years. The Voyagers symbolize both our ambition and the immense challenge of interstellar exploration. The Voyager mission stands as a beacon of human curiosity and resilience. These spacecraft, now silent ambassadors, carry our story into the cosmos, a reminder of our desire to explore the unknown. They have shown us that we can reach beyond our solar system, yet their journey underscores the vast distances that separate us from the stars. As we dream of interstellar travel, the Voyagers inspire us to push the boundaries of technology and imagination. Their legacy asks, can humanity follow in their path, not just with machines, but with our own presence among the stars. To journey beyond our planet, spacecraft must overcome a critical hurdle known as delta V, the change in velocity needed to travel through space. Delta V represents the energy required to shift orbits or escape Earth's gravity. To break free from Earth's surface and reach low orbit, a spacecraft needs a velocity change of about 6 miles per second. Escaping Earth's gravitational pull entirely demands even more, around 7 miles per second. This immense energy requirement shapes every space mission, dictating the size, design, and fuel demands of rockets, and remains a fundamental barrier to interstellar travel. Chemical rockets, the backbone of modern space exploration, face severe limitations in meeting delta V demands. These rockets burn fuel to produce thrust, but their exhaust velocity, typically 2 to 3 miles per second, is low compared to the speeds needed for deep space travel. As a result, rockets must carry vast amounts of fuel, often 90% of their total mass. The Saturn V, which sent astronauts to the Moon, weighed over 6 million pounds, yet only a small fraction was payload. This inefficiency, known as the rocket equation, makes chemical propulsion impractical for the vast distances of interstellar journeys. The rocket equation reveals a frustrating paradox. Adding more fuel increases a rocket's mass, requiring even more fuel to achieve the same delta V. For interstellar travel, where speeds of tens of thousands of miles per second are needed, chemical rockets fall short. A spacecraft aiming for Proxima Centauri, 4 light-years away, would require an infeasible amount of fuel, far exceeding the mass of Earth itself. This limitation confines chemical rockets to missions within our solar system, such as lunar landings or Mars rovers, leaving interstellar ambitions beyond their reach. To boost efficiency, engineers have employed gravity assists, using the gravitational pull of planets to slingshot spacecraft to higher speeds. The Voyager probes, for instance, gained significant delta V by swinging past Jupiter and Saturn, reaching speeds of 38,000 miles per hour. While effective, gravity assists are limited to the solar system's planetary paths and cannot provide the velocities needed for interstellar travel. They reduce fuel needs, but do not solve the core problem of achieving the immense delta V required to cross the vast gulfs between stars. Alternative propulsion systems offer hope for overcoming these constraints. Ion engines, which use electric fields to accelerate charged particles, achieve higher exhaust velocities, up to 20 miles per second, making them more efficient than chemical rockets. However, their thrust is low, requiring long periods to build speed, unsuitable for crewed missions or rapid launches. Nuclear thermal propulsion, heating hydrogen with a reactor, could double the efficiency of chemical rockets, but concerns about radiation and cost have stalled development. These technologies remain stepping stones, not solutions, for interstellar travel. The challenge of Delta V underscores the monumental task of interstellar exploration. Chemical rockets, while reliable for near-Earth missions, cannot bridge the cosmic distances to other stars. Gravity assists and emerging technologies like ion and nuclear propulsion offer incremental improvements, but they fall short of the breakthroughs needed. As we dream of reaching the stars, we must invent new propulsion methods that redefine the limits of delta V. Only then can humanity transform the rocket equation from a barrier into a gateway, opening the path to the cosmos beyond our solar system. In 1972, the Apollo 17 mission marked humanity's last footsteps on the Moon, a mere 240,000 miles from Earth. Since then, no human has ventured beyond low Earth orbit, a region just a few hundred miles above our planet. The Apollo program, driven by political rivalry with the Soviet Union, achieved extraordinary feats, landing 12 astronauts on the lunar surface. Yet, its high costs and risks, coupled with the completion of its political goals, led to its end. The question remains, why have we not returned to deep space in the decades since? After Apollo, space exploration shifted focus to low Earth orbit. The Space Shuttle program, launched in 1981, prioritized reusable spacecraft and the construction of the International Space Station, orbiting about 250 miles up. These missions emphasized scientific research and international collaboration, but confined humans to Earth's immediate vicinity. The shuttle's design, while innovative, lacked the capability to travel to the Moon or beyond, reflecting a strategic choice to focus on near-Earth activities rather than ambitious deep space ventures. Robotic missions have largely taken the lead in exploring the solar system. Probes like Voyager, Cassini, and Curiosity have traveled billions of miles, capturing images of Jupiter's moons, Saturn's rings, and Mars's surface. These missions are far cheaper and safer than crewed expeditions, offering scientific rewards without risking human lives. For instance, sending a rover to Mars costs a fraction of a crewed mission, which requires complex life support systems. This shift has allowed us to explore farther, but it has left human exploration tethered to the familiar bounds of low Earth orbit. Deep space poses formidable challenges for human explorers. Cosmic radiation from solar flares and galactic cosmic rays poses severe risks, increasing the likelihood of cancer and neurological damage. Unlike robots, humans require shielding, which adds significant weight to spacecraft. A journey to Mars, about 140 million miles away, would expose astronauts to radiation levels far beyond Earth's protective magnetic field. Developing effective shielding, such as water-based or advanced material barriers, remains a critical hurdle for safe human travel beyond our planet. Life support systems present another barrier. A crewed mission to deep space demands self-sustaining systems for air, water, and food over months or years. Current technologies, like those on the International Space Station, recycle water and air, but are not fully closed loop, requiring regular resupply from Earth. Experiments like Biosphere 2 in the 1990s revealed the difficulty of maintaining stable ecosystems. For interstellar travel, where resupply is impossible. Perfecting these systems is essential, yet current solutions remain inadequate for long-duration missions. Cost and risk further anchor humans to low Earth orbit. The Saturn V rocket, used for Apollo, cost over $1 billion per launch in today's terms and was not reusable. Modern rockets, like SpaceX's Falcon Heavy, are more economical, but still require immense investment for deep space missions. Political will also wanes without clear incentives, as seen after Apollo. The risks of radiation, system failures, and isolation make crewed missions daunting. These factors have prioritized robotic exploration, leaving human deep space travel as a goal for the future. The confinement to low Earth orbit reflects both practical and philosophical challenges. While robots have ventured to the edges of the solar system, humans remain bound by biology, technology, and economics. Yet, the dream of deep space persists, fueled by plans like NASA's Artemis program to return to the Moon. These steps may pave the way for Mars and beyond, but interstellar travel remains distant. The question lingers: can humanity overcome these barriers to claim its place among the stars, or will low Earth orbit remain our cosmic ceiling for generations to come? To reach the stars, humanity must transcend the limitations of chemical rockets. Advanced propulsion concepts offer bold visions for interstellar travel, pushing the boundaries of physics and engineering. These ideas range from nuclear-powered engines to speculative drives that challenge our understanding of the universe. Each concept aims to achieve the immense speeds, tens of thousands of miles per second, needed to cross the vast distances to stars like Proxima Centauri, 4 light-years away. Let us explore these revolutionary ideas that could one day carry humanity into the cosmos. One of the earliest radical proposals was Project Orion, conceived in the 1950s. This ambitious plan envisioned a spacecraft propelled by a series of nuclear explosions. Small atomic bombs, detonated behind a massive shield, would push the craft forward, achieving speeds up to 3% of light speed, or 5,600 miles per second. This could reach Proxima Centauri in a century. However, the 1963 Nuclear Test Ban Treaty and concerns about radioactive fallout halted the project. Orion remains a testament to the audacity of early interstellar dreams. Project Daedalus, proposed in the 1970s, took a different approach, using nuclear fusion. This unmanned spacecraft, weighing 54,000 tons, would fuse deuterium and helium-3 to generate thrust, reaching 12% of light speed. It could travel to Barnard's star, 6 light-years away, in 50 years. Yet, fusion technology remains undeveloped, and helium-3 is scarce on Earth, requiring mining from the Moon or gas giants. The immense cost and scale of Daedalus highlight the challenges of turning theoretical designs into reality, even for uncrewed missions. Nuclear thermal propulsion offers a more feasible near-term solution. By using a nuclear reactor to heat hydrogen propellant, This system achieves exhaust velocities twice that of chemical rockets, around 5 miles per second. NASA's NERVA program in the 1960s demonstrated its potential, but safety concerns and high costs paused development. Unlike chemical rockets, nuclear thermal engines could reduce travel time to Mars, 140 million miles away, but they lack the power for interstellar journeys. They represent a bridge to more advanced technologies. Solar sails provide an elegant, fuel-free alternative. These lightweight, reflective sails capture the momentum of sunlight, gradually accelerating without onboard propellant. A solar sail could reach speeds of several hundred miles per second over time, but its thrust weakens far from the sun. For interstellar travel, this limits their practicality, as a journey to Proxima Centauri would still take centuries. Solar sails excel for lightweight probes within the solar system, but scaling them for crewed missions remains a significant engineering challenge. A more ambitious variation is the laser sail, as envisioned by Breakthrough Starshot. Powerful Earth-based lasers would beam energy to a small, lightweight sail, accelerating it to 20% of light speed, 37,000 miles per second. This could reach Proxima Centauri in 20 years. However, the lasers require unprecedented power, equivalent to a nation's energy grid, and must maintain pinpoint accuracy over billions of miles. Collisions with interstellar dust also pose risks, making laser sails suitable only for tiny probes, not human-carrying spacecraft. Fusion propulsion holds immense promise, harnessing the power of stars themselves. By fusing hydrogen or helium isotopes, a fusion drive could achieve speeds of thousands of miles per second, potentially reaching nearby stars in decades. However, controlled fusion remains elusive, requiring extreme temperatures and pressures. Current experiments, like ITER, are earthbound and far from space-ready. The scarcity of fuels like helium-3 and the complexity of compact reactors make fusion drives a distant prospect, though they could revolutionize interstellar travel if realized. Antimatter engines represent the pinnacle of theoretical propulsion. When antimatter and matter collide, they annihilate, releasing nearly all their energy. An antimatter drive could achieve speeds approaching light, shrinking interstellar journeys to years. However, producing antimatter is extraordinarily costly, billions of dollars per gram, and storing it safely is a formidable challenge. Only tiny amounts are created in particle accelerators, far from the quantities needed for propulsion. Antimatter remains a distant dream, limited by our current technological and economic constraints. The Alcubierre drive pushes the boundaries of physics itself. Proposed by physicist Miguel Alcubierre, this concept envisions a spacecraft within a bubble of warped space-time, moving faster than light without violating relativity. By contracting space ahead and expanding it behind, the craft could travel vast distances in moments. However, it requires exotic matter with a negative mass, which may not exist, and energy equivalent to a star. The drive's stability and feasibility remain speculative, yet it inspires visions of a future where interstellar travel defies today's cosmic speed limits. Each of these propulsion ideas faces significant hurdles: technological, economic, and ethical. Nuclear and fusion systems raise safety and political concerns, while laser sails and antimatter drives demand breakthroughs in energy and materials. The Alcubierre drive, though captivating, borders on science fiction. These concepts require decades, if not centuries, of innovation to become reality. Yet, they reflect humanity's relentless drive to overcome the barriers of distance and energy, pushing us closer to the stars with each theoretical advance. Advanced propulsion is not just about technology. It is about redefining humanity's place in the universe. From the audacious nuclear pulses of Orion to the theoretical elegance of the Alcubierre drive, these ideas challenge us to dream beyond our current limits. While chemical rockets tether us to the solar system, these visions offer hope for interstellar voyages. The path forward demands breakthroughs in physics, engineering, and global collaboration. Can we harness these ideas to bridge the cosmic gulf, or will the stars remain forever out of reach? The answer lies in our pursuit of the impossible. Interstellar travel demands more than advanced technology. It challenges the very limits of human biology and psychology. Venturing beyond Earth exposes astronauts to harsh conditions that test the resilience of the human body. Cosmic radiation, a relentless stream of high-energy particles from supernovae and solar flares, poses a severe threat. A journey to Mars, 140 million miles away, could expose travelers to radiation levels far exceeding safe limits, increasing risks of cancer and neurological damage. Overcoming these biological barriers is critical for any mission to the stars. Radiation in deep space is unrelenting, unlike Earth, where our magnetic field and atmosphere provide protection. Galactic cosmic rays, traveling near the speed of light, can penetrate spacecraft walls, damaging DNA and raising cancer risks by several percent per year of exposure. Solar flares add bursts of intense radiation, threatening both crew and equipment. Shielding solutions, such as water tanks or advanced composites, add significant weight, complicating spacecraft design. Without breakthroughs in lightweight, effective shielding, long-duration missions remain a perilous prospect for human explorers. Sustaining human life in deep space requires robust life support systems. Air, water, and food must be recycled in a closed-loop system, as resupply missions are impossible over interstellar distances. Current systems, like those on the International Space Station, recycle 90% of water but rely on Earth for supplies. The 1990s Biosphere 2 experiment, aiming for self-sufficiency, struggled with unstable oxygen levels and crop failures. For a journey spanning decades, perfecting these systems is essential. Yet current technology falls short of the reliability needed for interstellar travel. Hibernation, or induced torpor, offers a potential solution to reduce resource demands. By lowering body temperature and metabolism, astronauts could sleep through long journeys, conserving food, water, and air. Research on animals shows promise, but human hibernation remains untested. Risks include muscle atrophy, blood clots, and organ damage during prolonged low metabolism states. Developing safe, reversible hibernation could revolutionize interstellar missions, but the technology is decades away. Until then, crews must endure the full duration of travel, facing both physical and mental strain. The psychological toll of interstellar travel is as daunting as the physical. Isolation in a confined spacecraft, far from Earth, can lead to stress, anxiety, and depression. Astronauts on the International Space Station, just 250 miles up, report challenges with confinement and monotony. A decades-long mission to a star like Proxima Centauri, 4 light-years away, would amplify these effects. The absence of natural light, limited social interaction, and the vastness of space could erode mental health, making crew cohesion and psychological resilience critical for mission success. For missions spanning generations, known as generation ships, psychological challenges intensify. Crews born aboard would never know Earth, living in an artificial environment with no external reference. Maintaining cultural identity, purpose, and social order over generations is a monumental task. Historical experiments, like isolated Antarctic bases, show that small groups can fracture under stress, leading to conflict or apathy. A generation ship, housing thousands for centuries, risks cultural drift or rebellion, threatening the mission's goal of reaching a distant star. Training and selection of crews can mitigate psychological risks. Astronauts are rigorously screened for mental stability and adaptability, but interstellar missions demand unprecedented endurance. Virtual reality and AI companions could simulate Earth's environment or provide emotional support, but these are untested for long-term isolation. Designing spacecraft with recreational spaces, artificial gravity, and natural aesthetics could help, but space constraints limit such features. The human mind, shaped by Earth's rhythms, faces an alien challenge in the void of interstellar space. These biological and psychological hurdles reveal the fragility of humans in the cosmos. Radiation threatens our cells, life support systems test our ingenuity, and isolation challenges our sanity. Hibernation and generation ships offer solutions but introduce new risks. Unlike robotic probes, humans require complex systems to survive, making crewed interstellar travel a daunting endeavor. Overcoming these challenges demands not just technological innovation, but a deeper understanding of our own biology and psyche, pushing the boundaries of what it means to be human. As we dream of the stars, we must confront our own limitations. The journey to Proxima Centauri, or beyond, requires us to shield our bodies, sustain our lives, and preserve our minds against the harsh realities of space. These challenges are not insurmountable, but they demand breakthroughs in science and resilience in spirit. Can we adapt our fragile forms to thrive in the cosmic void? Or will the stars remain a destination for machines alone? The answer lies in our ability to merge technology with the essence of humanity, forging a path to the distant reaches of the universe. Interstellar travel to stars like Proxima Centauri, 4 light-years away, may take centuries, far beyond a human lifespan. Generation ships offer a solution: massive vessels where successive generations live and die en route to a distant star. These self-contained worlds must sustain thousands of people for hundreds of years, carrying humanity's hopes across the cosmos. Yet, such missions raise profound ethical questions. Can we justify sending entire societies on a journey with no guarantee of success? And what moral dilemmas arise when the destination is a dream only their descendants will see? A generation ship must function as a self-sustaining ecosystem. Air, water, and food must be recycled with near-perfect efficiency, using hydroponic farms, algae bioreactors, or insect-based protein. The International Space Station, orbiting 250 miles above Earth, relies on resupply, but a generation ship cannot. The 1990s biosphere. 2 experiments showed how fragile such systems are, with oxygen fluctuations and crop failures. Maintaining a stable environment for centuries, without external support, demands technological precision beyond our current capabilities. Beyond technology, social stability is critical. A generation ship, housing thousands, must prevent conflict and cultural drift over centuries. Isolated communities, like Antarctic research stations, often face tension or apathy. On a ship where escape is impossible, disputes could escalate, threatening the mission. Maintaining purpose across generations is equally challenging, as later crews may question the goal of reaching a star they will never see. Education, governance, and cultural preservation must be carefully designed to sustain a unified society in the void. The ethics of generation ships center on choice. Those born aboard did not choose the mission, yet they must live and die for it. This mirrors life on Earth, where children inherit their circumstances, but the stakes are higher in a confined, artificial world. Is it just to impose a cosmic journey on future generations? Some argue it is no different from humanity's drive to explore, while others see it as a form of existential obligation, binding descendants to a goal set by their ancestors. This tension challenges our understanding of freedom and purpose. An alternative concept is the embryo ship, where frozen embryos are sent with robotic caretakers to raise them upon arrival. This reduces resource demands, as no living crew is needed during transit. However, it introduces new ethical concerns. Who programs the robots to raise these children, and how do they impart cultural values? Current artificial womb technology is rudimentary, and the psychological impact of growing up without human parents is unknown. Embryo ships sidestep some issues of generation ships, but create profound questions about identity and humanity. The risks of generation ships extend beyond ethics to practicality. A single system failure, oxygen, food, or social cohesion could doom the mission. Genetic diversity must be managed to avoid inbreeding, requiring careful population control. The ship's culture might evolve into something unrecognizable, potentially rejecting the original goal. Historical examples, like isolated religious communes, show how ideals can erode. Ensuring a ship remains true to its mission over centuries demands unprecedented foresight in design and governance. Generation ships embody humanity's ambition to reach the stars, but they force us to confront our moral limits. Can we create a society that thrives in isolation for centuries? Is it right to burden future generations with our cosmic dreams? These vessels are not just engineering marvels, but philosophical experiments, testing the essence of human purpose and sacrifice. As we ponder interstellar travel, we must weigh the cost of such journeys, not just in resources, but in the ethical legacy we leave for those who will inherit the stars. To explore the vast reaches of the galaxy, humanity may rely on machines that surpass our current capabilities. Self-replicating probes, often called von Neumann probes, offer a visionary solution. These robotic spacecraft would travel to distant star systems, harvest local resources, and build copies of themselves. Over millennia, a single probe could spawn a network of explorers, mapping thousands of stars. Such a system could reach Proxima Centauri, 4 light-years away, and beyond, carrying humanity's curiosity to the cosmos without the need for human presence. The potential of self-replicating probes is immense, but so are the risks. A probe that replicates uncontrollably could consume planetary resources, creating a gray goo scenario where entire worlds are dismantled. To prevent this, designers propose safeguards, such as limiting replication cycles or requiring Earth-based authorization. These probes would need advanced artificial intelligence to navigate, repair, and adapt to unknown environments. The challenge lies in ensuring their autonomy does not lead to unintended consequences across the galaxy's vast distances. Artificial intelligence is central to interstellar exploration. Current probes, like Voyager, rely on Earth for commands, but the light-speed delay, years for signals to reach Proxima Centauri, makes this impractical. Advanced AI could make real-time decisions, analyze alien worlds, and even repair probes. By simulating environments and learning from data, AI could adapt to challenges billions of miles away. Incorporating simulated emotions or ethical frameworks might guide their choices, ensuring alignment with human values in the uncharted realms of space. The concept of self-replicating probes raises profound questions, including the Fermi paradox. If such probes are feasible, why have we not detected alien versions? Advanced civilizations could have sent probes across the galaxy millions of years ago, yet we see no evidence. This absence suggests that intelligent life is rare, probes are difficult to build, or they are designed to remain hidden. The paradox challenges us to consider whether our own probes could inadvertently signal humanity's presence or disrupt alien ecosystems, raising ethical dilemmas. Self-replicating probes and artificial intelligence represent a shift in exploration, where machines, not humans, may lead the way. These technologies could explore the cosmos faster and more efficiently than crewed missions, unbound by biological limits. Yet, they demand unprecedented trust in autonomous systems. Can we design AI that remains loyal to our goals across light years? The answer will shape our galactic ambitions, determining whether machines become our emissaries to the stars or a cautionary tale of unchecked creation. As we dream of interstellar travel, we must consider Earth's fate. If humanity colonizes distant stars, will our home planet remain a vibrant hub or fade into a cosmic backwater? Optimists envision Earth as a cultural beacon, a historical archive, or a pilgrimage site for those born on alien worlds. Reduced population could allow nature to heal, restoring forests and oceans. Yet, a darker future looms. Earth could become a neglected outpost, its resources depleted as colonies thrive light years away. The bonds tying humanity to its cradle may weaken, reshaping our identity across the stars. The Great Silence, embodied in the Fermi paradox, deepens this reflection. Why have we detected no signs of alien life despite the galaxy's vastness? Intelligent civilizations may be rare, self-destructing before mastering interstellar travel. Alternatively, their signals might elude us, using technologies beyond radio waves. Self-replicating probes could already be here, hidden from our gaze. The paradox suggests humanity might be unique, or face a great filter, a barrier to becoming a galactic species. This silence challenges us to ponder our place in a potentially empty cosmos. The great filter could lie ahead in the form of technological or societal hurdles, or behind us in the improbable emergence of intelligent life. Interstellar travel, with its demands for advanced propulsion and resilience, may be this filter. If we overcome it, Earth could anchor a network of colonies, a testament to our ambition. If not, our planet might remain our only home, a solitary oasis. The Great Silence urges us to act with wisdom, ensuring our reach for the stars does not doom our cradle, but elevates it as the heart of a cosmic civilization. Interstellar travel is humanity's grandest aspiration, a journey fraught with challenges, cosmic distances, biological limits, and ethical dilemmas. From the Voyager probes to visions of generation ships, we stand at the threshold of possibility. Overcoming these barriers demands breakthroughs in technology and unity in purpose. Can we surpass the great filter to claim our place among the stars? Earth, our fragile home, awaits our answer. Let us pursue this dream with courage, forging a future where humanity not only survives, but thrives across the vast, wondrous cosmos. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.